In Protostructure 2022, we redesigned the loading system and developed a flexible loading editor. In this video, we will review the new load editor. The new load editor can be accessed in two different ways. In the first method, you can open the load editor for the active floor by clicking the load editor button on the loading ribbon tab. All members on the active floor are displayed in the load editor. Loads can be defined on these members and visually inspected. As the floor changes, the text on this button will also indicate the active floor. In the second method, after selecting a single member, you can open the load editor by clicking the Edit Loads button in the right-click menu or the contextual ribbon tab of the member. This way, only the element you selected and the loads associated with this element will be displayed in the load editor. Now, let's define the det and live loads on the floors. To define the loads in batch, select the first slab from the list on the structure tree and select the slab at the end of the list by holding down the Shift key on the keyboard. After selecting, right-click and open the slab properties with the Properties command. All selected slabs will be displayed in tabular form. Here, click on the header of the additional dead loads column. The entire column will become selected. Then click the column-wise Edit button and select the load you want to define in the provided input field. This load will be automatically assigned to all selected slabs. Let's do the same for the live load. We have defined det and live loads. Now let's define partition wall loads on slabs. For this purpose, let's switch to the plan view. The loading tab in the ribbon toolbar contains point line and area loads commands. You can use these commands to assign loads on slabs rapidly. Let's click on the line load command for the partition wall load. In the Properties window, there is a list that allows us to choose a wall type from the library. Let's choose a wall type from here and specify the thickness and height of the wall. Then, let's place the wall by picking 2 points on the slabs. We could also do this in the 3D view. In addition, there may be partially distributed loads on the floors, such as equipment or water tank loads. We can use the area load command for these. After entering the uniformly distributed pressure value, let's choose 2 points on the slab. So, the area load is inserted. After making these definitions, let's look at the load editor. As you can see, all the loads on our beam, including decomposed slab loads and the self-weight, are shown on the member. When you want to examine the loads separately, you can turn off the visibility of the load type you want from the filtering options on the right of the window. Let's close the wall load to simplify the image. You can turn off the slab area loads completely. Or, say, you want to turn off the display of self-weight loads and check the partial line loads. You can do this by deactivating the Show Self-Weights option in the View Options section. The loads that belong to the G-load case are displayed on the screen. Select the Q-load case from the list to see the loads in the Q-load case. The triangular and trapezoidal load profiles you see here are the loads transferred to the beams by the default yield line method. You can also decompose the slab by the finite element method. Close the load editor. Click on the Load Decomposition by Finite Elements button in the Loading tab and calculate the loads of this floor with finite elements. I'm not going into details of this in the scope of this video. Let's open the load editor again. As you can see, beam loads on this floor are calculated with finite elements. Load profiles are calculated as functions instead of triangular or trapezoidal shapes. If you do not want to see the distributed loads on the beams, you can turn off their visibility. Protostructure considers the self-weight of the beams as uniformly distributed loads between column faces. Loads decomposed from slabs to beams are defined as distributed loads and are displayed in a staggered manner with spaces between them. Instead of seeing the beam loads separately, you may want to see them as a combined single profile. For this purpose, you can press the Show Load as Merged button in the View Options section. Thus, a single profile is obtained by combining defined or distributed load states with the same load on the beams and shown in gray. This form of appearance does not affect the analysis results. It has only been developed so that you can examine the loads more easily. Now let's examine the usage areas of other commands and options in this interface. The display of elements can be set to solid view or analytical view. You can view the view with orthogonal or perspective projection from this section. With the transparency option, the appearance of the elements is shown in solid or transparent mode. The axis system defined in the model can be opened using the Show Axles command. Local axes of elements can be turned on or off with the Show Local Axes command. If you do not want to see the self-weights of your element, you can close this section. With the Auto Scale command, the defined loads can be scaled up or down. Frame labels, such as S1, frame end labels, I and J ends, load labels, load magnitude labels, and distance labels can also be turned on or off from this section. At the same time, label, size, and distance text sizes can be adjusted from this section. You can set whether to show surface labels or not. Loads defined on the members can also be turned on and off via the menu on the right of the window. Let's define the load by using the Load Types in the Loads tab. Select the load type from the ribbon to define a new load. The Load Identification command will be activated. Then, in which load state you want to define this load, select that load from the list on the left. Finally, specify the load properties and click on the member for which you want to define the load. Instructions will also be indicated in the yellow box at the top of the screen. For example, when you select a point load and click on any member, a point load will be defined on that member. Now let's define the wall load on the beam. Similarly, let's select the Wall Load command and enter the wall information from the Load Properties window that opens on the left. When you click on the beam, the wall load will be defined. If you wish, let's now define the distributed area load on a slab. To do this, click on the rectangular Uniform Area Load command. Let's turn off the visibility of all loads for easier identification. Then you can define the load by selecting 2 points on the member you want to define. We will examine other load definition options in detail when defining loads for different members. To edit a load that you have defined before, first select the load on the screen. Alternatively, you can select it by clicking the relevant load in the tree on the left. The selected load will turn red, and the Properties window of the load will automatically open on the left. Do not forget to press the Update button after making the necessary adjustments to the Properties window. Otherwise, the changes will not be reflected in the load. To copy the load, first, select the load you want to copy. After the load is selected, by painting it in red color, select the Copy command in the right-click menu. Then select the members that you want to paste the load by clicking one by one or by drawing a window. After the elements are selected, right-click and select the Paste Loads command. Even if the members are of different sizes, the bonded loads will adapt to the member. In projects with a large number of staff, you may want to focus on a certain section only. For this, select the members you want to work on one by one, or by drawing a window and use the filter command in the right-click menu. As you can see, only the selected elements remained in view and the others were hidden. To restore the view, simply right-click on an empty area and use the clear filter command. Now let's examine how we can use the load editor for rib and slab loads. The floors on the upper floor are defined as rib. When you examine the loads in the load editor, you will see that only self-weights are defined on the beams. No load is transferred from rib and cassette slabs to beams. Normally, you do not see the transferred loads. Because now in Protostructure 2022, rib slabs are always taken into account in the analysis model, and their loads will be transferred automatically during the analysis. Now that we have examined the load editor operating mode, which shows all the elements and loads on a floor, we can now examine how we can define them on an element-by-element basis. First of all, let's create the load states suitable for the loads that we will assign to the members. For this, let's click on the Load Cases and Load Combinations button in the Loading section. Let's leave the vertical loads and earthquake loadings as default from the Loading Generator section. However, let's close the loading generator by marking the soil pressure to define the earth load on the shear walls and the heat load to define the heat load for our building. The combination bag contains the load cases that will be created in accordance with the selected specifications. If you have loads that you want to define in different load states such as equipment load, water load, you can now create user-defined load states for them with Protostructure 2022. For example, in this structure, I don't want to include equipment loads in standard G and Q load cases. That's why I add a user-defined vertical load state from the Load States section. Let's enter a name and description for this load state. If we want, we can ensure that the defined loads are taken into account in the mass calculation. If this load is marked as a live load, depending on the floor it is located, it can be included in the seismic mass and earthquake calculations, or live load reduction can be applied to be used in the design. Let's define the user-defined vertical load state by clicking the OK button. Since it is a vertical load state, it will be automatically added to the top of the load state list. Now, I will create a user-defined horizontal load state for the water loads I will define. Similarly, I enter tags and descriptions. If this loading state will contain loads in the X direction, you must mark the prime direction. I don't want to make any definition of eccentricity into this load. When you click the OK button, you will see that the user-defined lateral load cases are defined above all other lateral load cases in the list after the vertical load cases. This sorting is done automatically by Protostructure. When you create user-defined vertical or horizontal load cases, these load cases are not automatically included in the combinations. You will have to manually edit the existing combinations to include these load cases. In addition, if you create a new bag with Load Preparer, the user-defined vertical and horizontal load states will be deleted, and Protostructure will allow you to transfer the loads assigned to these load states to a new load. Normally, it is recommended that you define load combinations and load states once before starting the project and not change them until the end of your project. Protostructure will not allow you to delete a load state with a load defined in it. If you still want to delete it, it will be deleted along with the loads in the load state. Now let's examine how to define a load on our beams. Let's choose the beam. Click the Edit Loads command on the Selection-Sensitive Contextual Ribbon tab or right-click menu. This time the load editor will open only for the selected beam. As you can see, the beam element is displayed in 3D with all the loads on it. When the editor is opened, the loads assigned to this beam in the first load state will be displayed in the order in the load state list. If you remember, I defined a user-defined vertical load state called G1 and Protostructure placed this loading state at the top. That's why this loading state is selected in the list. Since I haven't defined any load yet for this loading state, there is no load on this beam. From the list, let's select the G-load state automatically created by Protostructure. In the case of automatic G-load, the self-weights of the beams are also calculated automatically and acted on the beam as a distributed load between the columns. In addition to the self-weight, the loads transferred from the slabs to the beams in the case of G-loads will also be shown. If you have made the distribution of the slab loads using the yield line or load decomposition by finite element methods, you can examine them by clicking the options in the toolbar. Before defining a load, you need to make sure that the load state you want to use is selected from the list of load states on the left. If you want, let's get to know the load editor working screen. Global X, Y and Z coordinate axes are shown in the lower left corner of the window. On the beam are the local 1, 2 and 3 axes of this beam. Local axis 1 is shown in red, local axis 2 in green, and local axis 3 in blue. You can pan the camera by holding down the middle mouse button. You can rotate the view with the right button. In the upper right is the view cube. Using it, you can quickly look at the beam and loads from different angles. With the load state list on the left-hand tree, you can view loads in different load states and assign new loads to this loading state. The load editor includes some smart features so you can work in a practical way. For example, when you select the wall load command from the toolbar to define a wall load on the beam, other loads are temporarily removed from view. Now let's define a point load on the element by selecting the load state G1 from the list. Enter the label of the load you will define from the Load Properties window. If you do not want to enter a tag, Protostructure will automatically assign a load. However, for your convenience, it is useful to enter a descriptive and short tag. You must specify the direction to which the load will be applied, which is the most important parameter in the load definition. Loads can be defined on global and local axes. Force vectors can be defined in X, Y, and Z. Global axis directions are 1, 2, or 3 local axis directions. Let's enter 1 ton as the load value. If you selected gravity as the direction, positive values mean that a downward charge will be defined. However, if you have chosen global Z as the direction of the load, then you must enter a negative value to apply a downward load. The positive directions of the axes are shown on the screen. You can choose either percentage or distance as the measure type. In the percent option, 0% corresponds to the I end of the element and 100% corresponds to the J end. In the distance option, you must specify the absolute position of the element in units of length. If you enter 0 value, you specify the I end of the beam, and if you enter the beam length, you specify the J end of the beam. Since element lengths may be revised during the project phase, we can recommend you to use the percentage option. In this case, the length or position of the load will always be automatically updated as a percentage based on the element length, even if the element length changes. When you specify an absolute position, these values always remain the same. At this stage, simply click on one of the smart docking points on the element to define the point load. As an alternative load definition method, instead of smart points on the beam, you can click on the beam after entering a value in the position field. The position of the point load to be applied will also be displayed on the screen. If you want to define a uniformly distributed load on the beam from node to joint, you can use the uniformly distributed load command in the toolbar. Let's define a uniformly distributed load of 1 T per m in the direction of gravity. After entering the load label, load direction and load value, simply click on the beam. The preview of the load will be shown in gray when you hover over the beam. If you want to define a distributed load that does not cover the entire beam, you can use the partial uniform load command in the toolbar. Similarly, let's enter the load label and load direction. You can specify the start and end points of the load by clicking the smart points on the beam. Alternatively, you can specify the start and end distances and values of the load using the fields in the layout table. If you want to define a multi-point spread function load on the beam, you can use the trapezoidal load command. As with other loads, let's specify the load label and direction for this load type. Let's leave the default percentage option as the measure type. The default values for a trapezoidal load will come preloaded in the layout table. If you want, you can directly define this default load by clicking on the beam. Let's activate the layout option to change the load profile and load values. If you want, you can edit the values in the table here and add or remove new points. If you want to define faster, it is possible to automatically apply one of the ready profiles by pressing the load generator button. If you want to change a load that you have defined, first select the load on the screen or in the tree on the left. The selected load will be painted red. You can make the changes you want and apply the changes by pressing the update button. As you can see, the load has been updated. Now let's define a wall load as a G load on the beam. First of all, let's activate the wall load command. Let's choose a wall type from the wall library in the load properties panel that opens on the left side of the window. You will not be allowed to change the wall unit weight, total average load and wall thickness, which are suitable for the wall type you have chosen, by automatically filling them in. If you want to enter the wall load parameters manually instead of selecting from the library, leave the wall library field as user-defined. In this case, you will need to enter values such as unit weight and thickness yourself. There are two methods for specifying the wall height. In the first method, you can calculate and enter the wall height yourself. In this case, when the floor heights change, the height of the wall load will always remain constant. In the second method, you can enter the relative distance of the wall from the upper floor. In this case, when the floor height changes, the height of the wall load is adjusted automatically. Let's exemplify this. Let's define one of the beam wall loads, the first method, and the wall height by manually entering values h-start and h-finish. In another beam, let's define the wall load by entering the relative distance from the upper floor in the d-start and d-end fields. Now let's change the floor height. As you can see, the two wall loads behave differently from each other. The difference between these two methods can be explained in this way. The beams for which you define a wall load will be displayed by drawing a wall on them in both 3D and plan views. Thus, you can easily control the wall loads. When a wall load is defined on the beam, the wall load is defined between these columns, taking into account the widths of the floor columns to the right and left of the beam. For this, the element connection information must be up to date. In some cases, the connected element information on the right and left ends of the beam may not be up to date during modeling. Therefore, when defining wall load, column widths may not be detected, and wall load can be defined between beam nodal points. In such a case, you can use the update connection information command on the main screen. Then when you go back to the wall load definition, you can see that the wall load correctly detects the column widths at the right and left ends of the beam. If you want, you can manually change these automatically calculated offset values. To define partial wall loads, you can define between 2 points by clamping to the smart points on the beam. When you check the layout box to edit the partial wall load, the data fields of start offset, end offset and set wall length will become active. The initial offset is the distance from the I-end of the beam to the starting point of the wall load, and the end offset is the distance from the J-end of the beam to the end point of the wall load. To define a gap in the infill wall, let's examine another beam over a full height wall. After selecting the wall load, click the Edit Spaces button. The Wall Space Editor window will appear. Click the Add button here. A blank will appear in the drawing area. After selecting the space you have defined, you can delete it by pressing the Delete button. W in the upper part of the window indicates the width of the wall space, H indicates the height of the wall space, and X and Y indicate the offset from the lower left corner of the wall. If you disable the uniformly distribute loads of infill walls with openings option from the load regulator settings section in the settings section, a sensitive and detailed load profile will be created taking into account the positions and dimensions of the gaps you have defined. Let's cancel this setting and see how the load profile changes. As you can see, a detailed load profile was calculated considering the positions of the gaps. When you activate this setting again, the wall load is transferred to the beam uniformly by reducing the amount of space. You can use this option according to the need of your project. This setting is checked by default. If you want a detailed wall load profile to be used, you must also accurately define the wall gaps in their actual position. You can also define wall loads by dragging between 2 points in a plan or 3D model views. First, copy the wall load you want to define. Then right-click and select the Define Wall by dragging command. Identify 2 points on the beams on the screen and define the load. You can report all the loads assigned to the elements in the model by pressing the Report button in the Load Editor or by selecting the Element Loads command in the Drawings and Reports section while on the main model screen. While preparing the report, it is possible to perform detailed filtering according to the load type and load status. Now let's look at how loads can be defined on the columns in the model. After selecting the column, let's give the Edit Loads command. The types of loads that can be defined on the column are quite similar to those on the beam. Since the wall load cannot be defined on the column, there is no wall load between the command here. Also, unlike beams, moments can be defined only at the top points of the columns. Let us define a moment of 1 tm at the top of the column. After entering the load properties, it is enough to hover over the point and click. If you want to define a thermal load for elements, you must first select the heat load state from the load states list. While the heat load state is selected, the thermal load command will be active in the toolbar. In Protostructure, you can define homogeneous thermal exchange loads in the axial direction and gradient heat exchange loads around the local axis 2 and 3. While homogeneous heat exchange will create tension or pressure in the element itself, gradient heat changes will cause a bending moment. After defining the load in the column, let's close the load editor by clicking the OK button. Loads assigned to elements can also be seen in the Elements hint window. When you hover over the element with the mouse, the hint window will open. Let us now examine the loads that can be assigned to the shear wall elements. For this, after selecting the shear wall again, I click on the Edit Loads command. Unlike other elements, soil load can be defined as a shear wall. In Protostructure 2022 we have developed a handy tool for this. Activate the soil load command from the toolbar and click on the shear wall. In Protostructure, active-passive soil load acting on the ground shear in the basement of the building and structures such as pools and silos in the building can be modeled by defining these loads. Since the macro that automatically calculates the soil loads is the same as the retaining wall and pool macros in ProtAidTales, I will not go into detail here. You can calculate the loads automatically after determining the parameters such as soil profile, surcharge loads, and water table. However, if you choose basement wall as the shear wall type, you can calculate the special dynamic loads specified for the basement walls in the earthquake code. If you select the cantilever wall option, dynamic loads are calculated, as in the retaining wall module. The wall area load command is also used to define the distributed load on the openings of the shear walls. The only difference from the soil loads is that you have to calculate the load yourself. In this load type, you can also specify the distances of the load to the top and bottom of the wall. Thus, you can define the distributed loads on the wall side by side. For example, let's choose the load state we will use for the water load. Magnitude 1 describes the upper load value, and magnitude 2 describes the lower load value of the shear wall. If you want your load to be defined from a certain distance in the upper and lower sections. You can enter the values you want in the upper distance and lower distance fields after activating the settlement option. After entering all required values, click once on the screen to define the load. Let's exit the load editor by pressing the OK button. As you can see, the load is defined. In addition, you can define loads before and after joining to core shear walls in your model. Let's select the core wall and open the load editor with the Edit Loads command. Let's select Wall Area Load and define the load to one of the arms of the curtain and close the load editor with the OK button. When we separate the core curtain and look at loads of the curtain panel, you can see the loads that we defined in the core curtain on the independent curtain panel. Finally, let's examine the flooring elements. Similar to the other elements, let's select a tile and give the command Edit Loads. When the load editor is opened, depending on the load state selected in the list, the self-weight and additional fixed loads on the slab will appear as uniformly distributed area loads in the first place. To make other load definitions more comfortable, let's turn off the self-weights in the View Settings section. To define an additional evenly distributed load on the slab, click on the Full Uniform Area Load button. With this load type, evenly distributed loads that cover the entire floor can be defined. A preview of the load to be defined will appear in gray when you hover over the tile. You can place the load by clicking once on the slab. Rectangular uniform area load can be used for rectangular partial loads on the slab. After specifying the load characteristics, show 2 points on the slab. Interactively, the load will be drawn on the screen and will be defined when you select the second point. Alternatively, you can define the load corner points from the Layout section. With a polygon uniform area load, you can define loads other than 4 in the number of sides. For this, after specifying the load characteristics, start selecting the points on the slab in order. As the points are selected, the load polygon will begin to form. After selecting the points, right-click to finish the process and define the load. You can also define the load manually by editing existing points and creating new points from the Setup section of the Load Properties panel. Now let's define the parapet load on cantilever slabs. Select the cantilever tile and choose the Properties command in the right-click menu. After entering the load value in the parapet load field in the cantilever section of the Properties window, let's press the Update button. As you can see, the load is defined. We can do the same in the load editor. For this, let's give the Edit Loads command after choosing the cantilever tile. Let's add the linear load to the outer edge of the cantilever by showing 2 points with the Distributed Load command. Now that we've looked at how loads are defined on a member-by-member basis, let's see how to copy those charges between members. First, right-click on the element with the load defined and select the Copy Loads option. In the window that opens, specify the loads you want to copy and their load states. You can make multiple selections. Press the OK button. The loads are currently copied and are in memory. Select the member or members to which you want to attach the loads. Multiple selections can be made with Control, or more than one element can be selected by drawing a window. Right-click and select Paste Loads. Load copy operation will be performed on the selected members. You can do this in a plan or 3D views. To do the copying process quickly with keyboard shortcuts, select the member whose loads you want to copy and press the Ctrl+C keys from the keyboard. After specifying the loads you want to copy in the window that opens, select the target member or members to which you want to paste the loads. Paste the loads by pressing the Ctrl+V key combination from the keyboard. In this video, we discussed how to define the load on the members using the load editor. As I mentioned before, ProtoStructure automatically calculates all vertical and horizontal loads and affects the structure. With the load editor in ProtoStructure 2022, it has become much easier and more enjoyable to define the loads you want to the members in the load you want and in the direction you want. We will continue to review other new features in ProtoStructure 2022 in different videos. See you in the next video.